Now we're going to talk about the combination from molecular orbital theory of p orbitals. So we have 3 p orbitals, so we're going to have 3 molecular orbitals. When you have your p orbital that's along the internuclear axis, along the x-axis, they can only combine right here this one time. They can have a head-on combination. This forms a sigma p orbital. You would write sigma 2p, sigma 3p, depending on which energy level those orbitals are in. Now, this will have a bonding orbital, which is lower in energy, and an antibonding, which is a little bit higher in energy, where there's no electron density because of a node through the 2 antibonding spheres. So that's your sigma, that's your first one. I'm going to put this page right here so we can still see it later. Then we have the py. That's going up and down of your plane. Now, because these are next to each other, they can combine side by side. When you have a side-by-side combination, we already learned we can call that pi. So we have a pi 2p and a pi 2p star, where the internuclear distance is right here in the middle of the axes for the pi. Last one, pz. This is when you're going in and out of the plane, right? So like this. They also can combine twice. They have a side-by-side combination also forming pi 2p, where you have the pi 2p bonding and the pi 2p antibonding. So now that we've learned that, let's take a moment to construct an MO diagram, molecular orbital diagram, for oxygen. But what I should say is for these 3 atomic orbitals, they're all not in the same energy. So for all 3 p orbitals, we form sigma p, pi p, and another pi p. Due to this head-on collision of the pi x orbital forms sigma, and this large electron density compared to the pi's, sigma 2p is lower in energy, it's more stable. So when you have the energy diagram of your sigma and your sigma p comes first, and then your pi p comes after. Sigma is just a little bit more stable than the pi because it has a greater nuclear density due to that head-on collision combination of the atomic orbitals. So let's take a moment to go back to that magnetic behavior of O2. Let's draw the molecular orbital for oxygen. So try to pause this video and do that yourself. Hopefully you paused it. Let's see. I have 2s. Know how I'm only doing valence. You can do all of the orbitals starting at 1s, but we only need to focus on the valence electrons because that's how the molecules are made. So I have 2s, and then I have 2p. Note how I'm keeping them, since they're the same, they're homonuclear, in the same exact energy, because there shouldn't be any energy difference so that they can easily combine together. Alrighty, so then I have my sigma 2s and my sigma 2s star. So I take my 1 electron here, here, and here. Now I have my pi orbitals. So I've learned that I can make 3 molecular orbitals for my 3 atomic orbitals of my p orbitals, sigma and pi. Sigma is more stable, so I have sigma 2p and then pi 2p. Then for antibonding, sigma 2p is actually less stable for antibonding because there's almost no chance of finding an electron. So then you have pi 2p star and sigma 2p star. And then you would fill in your electrons. So you take 1 electron from here, 1 from here, pair first, then the next one. Boom, boom. Fill 1 in each before pairing. Boom, boom. And then you go up. Now take a moment and see. You have 2 electrons in the antibonding. This explains the paramagnetic behavior of oxygen. This is why when you put liquid oxygen into a magnetic pole, it attracts because it's paramagnetic due to the 2 electrons in the pi 2p orbital. Now let's take a moment and calculate the bond order. Number of bonding electrons, 2, 4, 6, 8, minus number of anti-bonding electrons, 2, 3, 4. 8 minus 4 is 4, divided by 2 is 2. Positive and greater than 0, this is very stable. Now another thing that we look at when we're doing molecular orbitals is writing the configuration, just like what we did for electron geometries and atoms. So I would write KK, this is symbolizing I'm talking about my molecule. Then sigma 2s instead of 2s2. Sigma 2s has how many electrons? 2. Then I have sigma 2s star. That also has 2 electrons. Then I have sigma 2p, 2 electrons. Then I have pi 2p with, how many electrons does that have? 4. Then I have pi 2p star with 2. So this is my molecular configuration instead of my electron configuration. So super important little bits to know. Making a diagram, the bond order, knowing what that means, and writing the configuration. With that said, let's do a practice problem. Where did I put it? There we go. So much paper. Draw the MO diagram and predict the bond order of lithium 2 plus and lithium 2 minus. Which is more stable? Do you expect these molecules to exist in gas phase? So let's look at that. So I have lithium 2 plus and then lithium 2 minus. I'll have lithium on both sides. I'm going to try this one first. Now the plus is only going to go to one of them. Doesn't matter which one because they're the same exact molecule. Now, lithium has how many electrons in valence shell? 1. So if I have a plus, I'm not going to have any electrons here. And 1 left over right here. Then I form my sigma 2s and my sigma 2s star. And I take my 1 electron, boom, and then that's it. My bond order to figure out the stability would 1/2 times number of bonding electrons is 1 minus number of anti-bonding is 0. So that would be 1/2. Let's try lithium anion. Li, which would have a minus, and then regular lithium. Now, this minus means I gained an electron, so this would have 2, and then I have the 2s with the 1. So then I form my sigma 2s, sigma 2s star. Take my 1 electron from here, and pair it, and 1 more up here. So then my bond order is equal to 1/2 times 2 bonding electrons minus 1 anti-bonding. 2 minus 1 is 1, 1/2. So which one is more stable? Either. They're both equal in stability because they both have a bond order of 1/2. Therefore, they both exist in gas phase. Now, we talked about everything that's important, but there's a little bit of a difference when we have boron, carbon, and nitrogen in our second period diatomics and oxygen, fluorine, and neon. Now, if you look at this arrangement, see how you have sigma 2s, sigma 2s star, sigma 2p, pi 2p, pi 2p star, sigma 2p star. This never changes. However, when you have boron, carbon, and nitrogen, the arrangement of just the sigma 2p and pi 2p changes. This is because of something called sp mixing. We know that boron, if we look at the 2p orbital, has just the 1 valence electron. Carbon has 2, and nitrogen has 3. Oxygen will be the first one that has a pair in it, and we know fluorine has pairs, and the nitrogen, neon is all paired. So because these three have either empty orbitals or unpaired orbitals, they undergo something called sp orbital mixing. And this makes the MO diagram between boron, carbon, and nitrogen diatomics different than the original MO diagram that we've learned. So the molecular orbitals are formed from linear combinations that include all of the atomic orbitals that are relatively close to each other in energy and of the correct symmetry. So we know these are in the same energy because they're homonuclear. Linearly combine will lower because of bonding, increase because of antibonding. When sigma 2s and sigma 2p wave functions combine in a way that the sigma 2s is more stable, lower in energy, and sigma 2p is less stable, higher in energy, the sigma 2p will sit above the pi 2p orbitals. This sp mixing is negligible for oxygen, fluorine, and neon because the 2p orbitals have some paired, which raises the energy and dismisses the mixture. As you go to the right on the periodic table, you know that the nuclear charge increases and the atomic radius decreases, and all of the orbitals lower in energy. So you have the atomic orbitals that are lower in energy as we go to the right because they're more electronegative. As we go to the left, more for boron, carbon, and nitrogen, our atomic orbitals are less stable and higher in energy. This higher in energy causes the sigma 2s here and sigma 2p to combine in a way that actually makes them push further away from one another. And when they push further away from one another, the sigma 2p comes first because of sp orbital mixing. Because the orbitals are closer together, since they have unpaired electrons and empty orbitals. So sp mixing is really important because of the energy difference with these structures. So the arrangement of the atomic molecular orbitals is pi 2p first and then sigma 2p for the boron, carbon, and nitrogen diatomics. So with that said, let's do the molecular orbital for N2. Let's take a moment to do that. So we have the energy, nitrogen 2s, 2p. Then I have my p orbitals, which I know I have 3, sigma and 2 pi's. Now, the s and the p have mixing because of the unpaired of the p electrons, making the s and the p energy difference very small within one another, and those wave functions combine in a way that makes the p orbitals more stable, the s a little bit less stable. This does not affect the arrangement of the antibonding. The antibonding still split so far above that the sigma 2p still stays above the pi 2p, just like the original structure. 1 electron here, 1 electron here, pair, you pair. One way to check that you have all your electrons in your molecular orbital is by counting. You know that nitrogen has 5 on its own, so the molecule should have 10. 2, 4, 6, 10. Perfect. Let's write the configuration for this. You write your molecule just like you would write your atomic orbital. 1s is my molecular orbital, 2s, and then I have 2 electrons. Now, what's my bond order? 1/2 times 1, 2, 3, 4, 5, 6 minus oops, I just realized 2, 4, 6, 8. Don't have 10 electrons. 1, 2, because I'm missing, I did 1 here, 1 here, 1 here, and another 1 here. I'm missing my sigma 2p. So I actually have 2, 4, 6, 8 bonding electrons minus 2 non-bonding. 8 minus 2 is 3 divided by 2 is 8 minus 2 is 6, divided by 2 is 3. So this is also very stable. So another way sometimes when you're doing the different calculations is you can notice different mistakes. So this is molecular orbitals. What's happening is the atomic orbitals are just summing together to make molecular orbitals. When they're in phase, they make bonding orbitals. When they're out of phase, they make anti-bonding orbitals. Sigma, because of the head-on collision, is more stable than pi. When you have the p orbitals, you always have 3, the sigma and the 2 pi's. For boron, carbon, and nitrogen, due to the empty orbitals and the unpair of electrons, the energy causes the sp orbital mixing to push sigma to s and sigma to p further apart from one another and changes the arrangement of the molecular orbital diagram.